Welcome this morning. My name is Rick Cummins. Been with Gensco almost 11 years. This summer it will be 11 years, and have been in the industry a lot longer than that. And coming from South Louisiana, I'm very familiar with humidity problems. And I bring this subject up here as we begin our summer season coming up soon, because the last couple of years we have run into the end of the summer quite a few issues revolving around humidity in homes. It's not something most people have had to deal with, and it depends on what kind of weather we have every year, but we have had a couple where we have had some high dew points at night, and it has led to some humidity concerns and issues that arise because of the humidity concerns in a lot of residential applications. And that's primarily what we're talking about today, residential issues. And the biggest problem we have if you're living here on the west side of the Cascade Mountains in what we call the wet zone or the marine environment is that we don't get really hot. And the times we do get really hot, the humidity is pretty low. We get California weather when it's really hot. But we have had times where, yes, the dew points are up and we have some humidity concerns inside the house, but we don't have a cooling load. And we're going to talk about why that's an issue. So, what is humidity? Well, everybody's seen windows that look like that, um, especially in the wintertime when it's got a temperature difference on one side or the other. All you need is a surface that is below the dew point of the air around it, and you're going to get condensation. And there are two types of humidity. One everybody is familiar with, relative humidity. We talk about this a lot. Oh, I feel muggy because the humidity is up. Well, relative humidity, relative, is the ratio of the amount of water in the air to the amount of water the air can hold. And it's measured as a percentage. If we have 100% humidity, it can't hold any more physical water, and it will begin to condense out of the air. When we get to maximum saturation in a cloud, it begins to rain. Something similar can happen inside your home. You may have even been in places where you saw actual condensation form on surfaces somewhere. I never forget the day I went to a problem house in Louisiana where, as I walked into the house, it was 65 degrees on a 95-degree day. And the humidity level inside the house was 78%, and my finger left marks on furniture because they were wet. And that was the result of someone replacing a 36,000 BTU AC unit with a 60,000 BTU AC unit, which is the basic problem we have here. Not that we're putting too big of an AC in, we just don't have a load because we're putting AC in that's basically sized off the heat pump, the heating side. So relative humidity, everyone is pretty familiar with, you customers are familiar with, and we talk about it all the time. And again, that's a ratio of the amount of water in the air to the amount the air can hold. One example would be these images where we get to 100% humidity and all we need is a little bit more and we're going to start having condensation. 90% humidity, very muggy. How much the air can hold versus how much is in the air. Then there's another type of humidity. This one comes a lot into play in engineering because it actually involves water and how much do we need to remove. The other type of humidity is called absolute humidity. And this is the actual amount of water in the air measured in either grains of water per pound or pounds of water per pound of air. When we talk about dehumidification, we're talking about physical amounts of water we're going to remove from the air. Absolute humidity represented here. If you count my little water drops, there are 35 of them in each of these squares. But as you heat water, or sorry, heat air, it expands. thus lowering the relative humidity. Warmer air can hold more physical water than colder air. If we chill the air sufficiently, we will start to condense moisture out of the air. So this is a representation of, again, absolute humidity, the physical amount of water that's in the air. And when it comes to humidity, one of the big things is your thermal comfort. As is explained here, it is defined as that condition of the mind, it's all in your mind, which expresses satisfaction with the thermal environment. I feel comfortable. I'm thermally comfortable. Or I don't feel comfortable. It feels muggy or it's super dry. It could be the complete opposite. And the goal of every sales engineer or anyone who's selling is design a system that provides thermal comfort to the people living in the house. You want them to be happy, and if they're happy, you get referrals. If they're not happy, you get phone calls. And most of this comes down to sizing properly and air distribution. So what factors can influence a person's thermal comfort? Temperature, and the big one, humidity, thermal radiation, sun's shining on me, I'm going to warm up. Airspeed, if there's a fan blowing air on me, it's going to help cool me off. Your personal activity, are you very active or are you just sedate and watching TV? There's a huge difference between doing housework and not doing anything. And what kind of clothing are you wearing? So a lot of things play into a person's personal comfort level. And humidity has a big one because one of the things that's going to actually, you're going to see adds humidity to the air is transpiration out of a living person's or entity's body, where we actually evaporate water through our skin. And that can provide a cooling effect. The lower the humidity, the cooler you feel. The higher the humidity, you don't feel that cool. Temperature has a play into that too, but humidity has a bigger play because we cool our bodies with that transpiration or perspiration, something that's going to take water and give us a cooling effect from the evaporation of the water into the air. Temperature and humidity, again, play the biggest role in thermal comfort. Obviously, if the temperature is very warm, you're going to feel warm. But you could have a situation, and this is pretty common. It's 74 degrees and the humidity level in the house is 40%. I feel a whole lot better than if the temperature is 70 degrees and the humidity is 60%. You're not going to feel as comfortable. Transpiration is the process of water vapor transmission from your body via pores in your skin, and it produces an evaporative cooling effect on your skin. Makes you feel cooler the greater the rate of evaporation. So the lower the humidity, the greater that rate is, the cooler you're going to feel. Perspiration, like transpiration, but at an accelerated level. As you start doing some kind of physical activity, your body is going to begin to heat up, and to compensate and cool down, you will actually begin to perspire, which is, again, an accelerated level of moisture leaving your body. Transpiration is one of the reasons, even though when you live out west and hey, you have to really hydrate when you work in Louisiana. But working out here in the West, you don't feel like you need to hydrate because it doesn't feel that hot. And you're not sweating, but you are transpiring and you are losing physical water out of your body. So you do still need to maintain your hydration levels, even when you don't feel like you do. And what is a comfort zone? This is a bit of contention as to what actually is the comfort zone. According to ASHRAE, it's this little green trapezoid in the middle of my psychrometric chart. And it's defined as a dry bulb range in winter of 68 to 77 and a relative humidity of 25 to 60%. And in summer from 73 to 82, really. Relative humidity is 25 to 60%. I would say 82 at 25, and I don't know about 73 at 60% humidity. I really want that to be a little lower. But this is what's defined as the actual comfort zone that we're trying to design systems to stay within. 30 to 60% relative humidity and a temperature range somewhere between 68 and 80, basically. And again, a little exploded view of that and those temperatures that ASHRAE defines as the comfort zone. The optimal zone for humidity falls between 40 and 60. And the reason for that is we're going to have a big one is your health. Less bacteria, viruses, fungi, mites, respiratory infections, allergic reactions, asthma. Everything you see in that little blue columns, that is what we're trying to achieve. The closer we get to the middle, I think is the ideal position, somewhere around 50%. We want to avoid any situations where we're getting over that 60% mark. 60% is the accepted demarcation line. Where above that, we begin to grow biological things that are going to affect us. And one of the ones that you guys may have heard of and may have dealt with is something called the dirty sock syndrome, where you're getting odors coming from your air conditioning unit. And this is outgassing from dying biological material or dead biological material that has been rehydrated by the condensate that's built up in the coil or drain pan. And it can produce an odor that people don't like. And again, starts around 60% relative humidity. And the higher you are above that number, the faster the growth rate. That's why we want to try to keep the house below that number. We can avoid having unpleasant things happen. Now, even if we keep the house below that, we can't always keep our unit below that, and we'll explain some of that also. High humidity, and the main thing I'm dealing with here today. Not going to talk about low humidity. It's something we have to deal with during the winter months when we're heating the air. But high humidity, it can create a breeding ground for mold and mildew. It can damage surfaces in the structure, even the structure itself can be damaged by moisture. The health problems, metallic corrosion, and reduced air quality. Everyone can probably agree when the humidity is low, the air smells better than when the humidity is high. Now, where does this humidity come from? We don't live in a humid environment. When we're hot outside, our typical humidity outside is in the below 40%. It's not like where I come from. The reason I decided to move to Washington one night doing a proposal for someone, my AC kicked on. I looked at my weather station display next to my desk and it said 88 degrees, 96% humidity. This was the outside ambient conditions. And that was at midnight on August the 3rd, 2006. I moved here in 2007. So people from within the home, the average human will contribute over 40 ounces of water per day to the indoor environment. Due to aspiration, you breathing. If you go outside in cold weather, you see the vapor and the mist coming out of your breathing. That's happening inside the house, even though you can't see it because the temperature conditions don't allow it. Transpiration through your skin or perspiration if you are at an elevated physical activity level. Pets can also contribute approximately a quarter ounce of per pound of body weight. A 75, you got a big dog, 75-pound dog is contributing 18.8 ounces per day. And that can vary on day, it can vary on what the conditions are within the house. If the humidity level is high, you have less transpiration. If the humidity level is low, you're going to have more transpiration. Showering. On average, a 3-minute shower contributes 0.44 pounds of water vapor into the home. That's 6.75 ounces of water. A 15-minute shower releases 1.76 pounds of water vapor, 27 ounces. You also have to take into account the residual water that's left in the shower, which can be another 4 ounces of water when it evaporates, and the towel that you use to dry off, if left hanging, will contribute another 3 ounces of water. Now, where did I get those numbers from? I got these other numbers from studies that I found. These numbers here at the bottom is me running my shower, letting it sit there till the water that was going to drained down, and then wiping it dry with paper towels and weighing them. I did the same thing to the towel. I measured it dry and I measured it after drying off. And this is what I came up with. So every time someone takes a shower, we're looking at anywhere from 10 ounces of water to 35 ounces of water added to the air every time, every person. Every time you run your sink just to rinse something, all the water remaining in the sink is going to evaporate back into the air. If you have plants in the house, on average, 85 to 95% of the watering that you put in the plant returns to the air from the plant's transpiration. And the studies indicate that evaporation from the soil around the plant is negligible and almost not measurable. Then cooking. If you boil a pot of soup, 31.3 ounces on average. Frying something, 5 ounces of water. Steaming, almost 10 ounces of water going into the air. So here in the Western United States, we don't have infiltrated moisture on times when we need to do air conditioning. It's all coming from inside the house. And according to ASHRAE, if you wanted to maintain a 55% relative humidity condition within a home, you do not need to have outside air introduced to displace that, because our outside air humidity is so low already. If you want to get to 50%, you will need to remove some physical water. Now, removing that water vapor from inside a home requires either sufficient ventilation to displace the volume of air within the structure, and that has been pegged at 5 to 6 air changes per hour. So if we're talking an ERV, in an 1,800 square foot house, which 8-foot ceilings is 14,400 cubic feet, we need to have 5 air changes divided by 60 minutes in an hour. That would be 1,200 CFM of ventilation to completely displace the air in the house 5 times. That's one way to deal with humidity, and that's pretty excessive. The second way is a mechanical mean, either through air conditioning, because the benefit of air conditioning is dehumidification. It's one of the side effects, or a dehumidifier. Now, in order for mechanical cooling or air conditioning to remove moisture from the home, the system must operate. The indoor coil must reach a temperature lower than the dew point temperature of the entering air. The greater that difference between the coil temperature and the dew point of the air, the greater the rate of condensation. Now, this is one place where mini splits in the Mitsubishi world aren't that great at this part. Their target coil temps are not 40 degrees like universal standard in air conditioning, how it's been since I got into this industry. It's more like 50 degrees. We're not going to do as much condensating on the coil because we don't have a huge difference between coil temp and the dew point. Where if we had a 40-degree coil, and sometimes we do, there are instances where we are much colder than that. but that's not what we're targeting. So we need the coil to have a temperature lower than the dew point. Moisture must begin to condense on the coil. It must coalesce to a sufficient size droplet that gravity comes into play. And then it must have enough quantity that it can actually be pulled down into the drain pan and enough that it will actually drain out of the unit. And the big key to this one and why we have humidity problems in cooling in some cases here in the Northwest is that this takes time and we don't have a load. So how does it work, mechanical cooling? This is an example of, say, a house at 76 degrees, 55% relative humidity. The dew point is 58.7. All we need is our coil to be below that to begin to condense. And if we can get a really cold coil, 40 to 45 degrees, we're going to condense faster. Now, within that air, the absolute humidity is 73.7 grains per pound of air. And to put that in perspective, there are 7,000 grains per pound of water. We need 7,000 grains to equal 1 pound. So if we take the difference, they are 73.7 and 55, we have 18 grains per pound of air circulating after we have done dehumidification. And I got my number wrong over there. That was 55.7. And this particular unit, a GS12, 343 CFM with a wet coil, that's circulating at that condition, 76 and 55%. It occupies a volume of 13.72 cubic feet per pound of air. That would equal 25 pounds of air circulating per minute. And if we multiply that times 60 minutes in an hour, we are removing 27,000 grains per hour. Divided by 7,000 is 3.84 pounds, divided by 8.34 times 128. We are removing approximately 0.46 gallons or 59 ounces of water, physical water, if this unit ran for 1 hour. Let's sink in. 1 hour of running, we could remove 60 ounces of physical water. Pretty good, but we have to run. To run, we need a load. Another situation, and probably at 76, if we have a set point of 70 to 72, we are going to run if we have a load. But what if we're already cool in the house? 70 degrees, 62% relative humidity. This is an uncomfortable number. You're not going to feel good at this. 67.7 grains per pound. And if we ran the unit with the same BTU output, we're going to end up with 49 grains. Again, we're over 18 grains per pound of air circulating. We're still removing pretty good water, 62 ounces if we could run for 1 hour. But with a 70-degree dry bulb, and that's what every unit operates off of, dry bulb, we're not going to run. So we're not going to get rid of this water, and that humidity is going to remain high. So this is where we run into a problem in the Northwest in our marine environment because we don't have a load. We can't keep the unit running long enough to actually remove water. And again, we're already cool. And I've run into this myself in my house. And one of the things how I deal with that, and I'll show you when we get to the end of this, is the other way that you can deal with the humid issue or a humidity issue. I need to point out that in Mitsubishi units, it takes 20 minutes of running for a unit to reach its steady state efficiency. 20 minutes. In a unitary system, that's only 6 or 7 minutes. But for us, 20 minutes before we're at optimal coil temperatures. It takes more than 20 minutes of runtime before we are likely to even get sufficient condensation to collect in a drainable quantity. So if we run for 10 minutes and stop, guess what happens to the water that did condense on the coil? It evaporates back into the air, except we've cooled the air. And if we go back to the absolute humidity, We've cooled the air. We've caused it to contract, but we have the same amount of water in it. Our humidity level goes up. We're actually making it worse by cooling the air. And this is an actual case history to illustrate that point. I went out to a job site where a homeowner had a complaint of dirty sock odor from an indoor unit. It was an FH06, part of a 3C30 multi-zone system. The bedroom was occupied by an 8-year-old boy who had asthma, and the odor from his unit was triggering asthma attacks. I did a quick survey of the room based on its size, its exposure, and came up with a load calculation on that particular day of only 500 BTUs of cooling. I placed that unit in emergency cooling with its emergency operation push button on the front of the unit. The initial conditions were 74 degrees and 54% humidity. And after 10 minutes of operation, that room temperature was down to 64 degrees, 66% humidity. Humidity went up. And the total cooling output, this is not unusual, double what it's rated to do. Ductless units overproduce. The unit was allowed to operate another 10 minutes and the room reached 57 degrees. That's a 17-degree drop in dry bulb temperature, and my humidity broke 70% in the room. I stopped the test, and I went outside before I left this house to check and see how much water actually came out of that drain line, which terminated near the ground. This was on an outside wall, went out the wall, down a piece of pipe to the ground, and there was zero water there. And I dropped the temperature in the room, but didn't physically remove any water, and the humidity level went through the roof, and hence I'm going to have biologicals growing. And this is what produces the odor. In order to prevent that, I need the humidity to be a lot lower in that room. This is real. I've run into this. This is what the worst one probably I ran into, with a unit being oversized to start with. Never runs long enough to do anything but raise the humidity. I advise this homeowner to never use the unit for cooling. Go to Home Depot, get a standalone dehumidifier, put it in the room, and only operate that. And it must have worked because I never heard back from them. And in really bad examples of high humidity conditions within a home, you're going to run into this. You're going to have levels of biological growth like this in this unit, inside my unit. And some of you may have already seen this or dealt with this in a job site. If I went back and looked at the conditions, psychrometric conditions, when you're coming into the unit, yes, that humidity might only be 54%, 55% coming in. But once I've cooled it, even if I have physically removed water from the air, humidity level behind that coil and on the blower wheel, because our blower wheel is in the cold side of the coil, is going to be 90% and higher. It could approach 100%. In that case, we're going to be wet in there constantly, and you're going to get this. This is an actual unit that I showed at our dealer meeting, I don't know, 4 years ago. Actually 5, I think right before COVID, when we did it up at Tulalip. From a contractor on Whidbey Island. And this was a unit that he had previously cleaned 6 months before. This is a high humidity issue within the house that can't be solved by running my unit because it won't run long enough. That has to be dealt another way. And the whole purpose of me trying to get you guys here today is you have to consider that you need another means of dealing with the humidity than thinking that my unit is going to do it for you. So pretty bad case here from living in that cold environment. Black mold. This is what it looks like under a microscope. It looks like cauliflower or broccoli. Pretty bad for anyone's health. especially if they already have health conditions. And you want to avoid this. And one way to do that, if you can't do it with the air conditioner, if we're oversized, which again, you're sizing my unit for heating, and your cooling load is typically going to be somewhere between 40 and 60% of your heating BTUs. So just getting the heat pump installed, I'm double the size I need to be for cooling. I'm not going to run long enough to dehumidify, if that is the case. And a lot of this is small walled units, wall mounted units, or ceiling cassette units in tiny bedrooms that never run. A better option for this, and this is money in your pocket if you can identify this up front, or at least raise a possible concern with the homeowner that they may have to look at other means for controlling humidity, is a dehumidifier. A dehumidifier works by taking the air through an evaporator coil, removing physical water, and then reheating it with the condenser coil and bringing it back up to near, or sometimes a little bit less or a little bit more than the actual room temperature. But we physically can remove water without changing the room temperature. I can't do that with cooling in a system because I'm going to lower the temperature. So you may consider a dehumidifier as a better option if you run into humidity problems. And if you have a unit growing mold like that previous picture, you have a humidity problem or a severe sizing problem, which could create the humidity problem. So if the sizing can't be avoided, you can't size it correctly, then you may have to look at secondary means to control the humidity within the house. It could be a ducted humidifier for the whole house. They come in different sizes, rated by pints, 120 pints. These are some from Gensco's catalog. There's a 65 pinter. And another option would be something that's standalone. There are many different types of these with many different capacities. I personally myself have a standalone dehumidifier that can do 65 pints of water. I don't have it. I just roll it out when I need it. And it hasn't been very often. I've probably used it 10 times in 18 years. But I can't run my air conditioner. It's already too cool. But the humidity level, it makes it uncomfortable. It's all I do, drag it out. Now, this is what we're talking about, humidity. And I know this wasn't a big slideshow, but I will open this up for questions if anyone has any. Let me click some of these other people who just got in late.
I have a
Any?
question. How would you
Yes.
recommend sizing small bedrooms, like the scenario you were just giving? Would you just say, don't use it in cooling at all, but you can go ahead and use it in heating, or would you just not put one in a small bedroom?
That's an excellent question. And we go back to sizing. Okay. If you can get away with a one-to-one Mitsubishi oversizing at 50%. You can't get away with oversizing at 50% in a multi-zone. The best you can get away with is 15 to 20%. But in many cases, these units are 200 to 400% oversized for the load.
Yeah, I
So
feel like mo
small bedrooms are a problem. They are. What
most
I'd
bedrooms
rather
I see are
do,
like 2K BTUs is the
yeah.
most they need.
So let's say I have 3 bedrooms. Let me put a small 9K ducted unit and spread that around rather than sticking a 6 in all of those rooms. I do deal with that problem from a customer satisfaction standpoint, and it's unsolvable in many cases. Completely. One of the worst ones I've seen is 3 bedrooms that had a cumulative load of about 4,000 BTUs, and he had 27,000 BTUs in those 3 bedrooms. His biggest
Okay.
complaint was overheating, not so much the cooling. He's right on the water. I don't even know if he ever needs to run his cooling. But oversizing in small rooms like that one that I gave an example of, yeah, I can't solve that with cooling. That's going to require secondary dehumidification. And that may be a conversation you have to have with a homeowner that where you are, you're not going to have much cooling load and humidity could be a problem. You may consider us coming and doing something else. Hey, here's an option if you need it for a whole house dehumidifier. Yeah, that's money up front. And hey, he did tell us about that in the beginning, and now I think we need it. But when they don't know about it, and then you come in and say, well, I did this. And so understanding this part and that it can become a problem is key to being profitable and not having a bad review or having to go back and do stuff at your expense later. Just understand that every time we're dealing with a humidity problem here in the Northwest, it's either going to be created by interior conditions or the fact that we're short cycling the air conditioner. And that's generally the sizing part. And in many cases, like, you can't avoid it cooling oversizing because we're sizing it for the heat load. But if the heat load has been oversized by 200 to 300%, then the cooling is oversized by 700%. That can be a problem. It's a good question.
Gotcha. Thank you.
I have a couple questions. Is the humidity issue one of the reasons why Mitsubishi recommends like how they always have the fan running on low speed?
The fan always runs in a Mitsubishi unit primarily because by default we're using the return air temp sensor to control space temp. And if we're not moving air, we can't sense the space temp.
Okay. And
Okay,
then
now that process of doing that can contribute to the humidity issue because any moisture that condensed on the coil gets pushed back in the air.
yeah, it makes sense. So and then another thing is, are they ever gonna come out with like a 4K head for MMP?
This morning in a meeting, I asked for a 2.5K head.
Yeah, I mean
Like I
something
really
smaller
need
than a
one.
6.
I know. Not that to my knowledge, are they going to do? I heard 2 years ago they were looking at a 4K. I haven't seen it. We have a 4K in our city multi lineup.
Yeah, that's why it doesn't make sense why they don't have it on the MMP stuff.
Well, in a city, let's say I do a smart multi with city multi indoor units and I do a 36K unit. I'm not limited to 4 heads there. I could put 11 heads if I have city multi equipment
Yeah.
and 4Ks. I could do 11 4K heads on that system. I just want to make sure you guys understand that if you run into this in August, and it's probably going to be that time of the year, August to September, when we start getting those higher dew point nights and we can't control the humidity from infiltration or ventilation.
Hey, Rick.
Yep.
Hey, I was actually at a customer's residence with a company last week with this exact scenario. They claimed that and they're right on the water in Kirkland, claimed that the 24K high wall was literally dripping water out of it because the drain pan couldn't keep up with the amount of moisture that was coming off of the coil.
Just sure that was coming off the coil and not condensation developing on like the louvers
On the
because of
back
a
of
high dew point in the room.
or on the back of the filter, and running down
Yeah.
the unit. Yeah, that sort of thing. That was accounted for. So what's the best recommendation in scenarios where we're about to approach customers that have a scenario, they're on the water, and again, it was August, just like you mentioned, which caused me to ask the question, was when they first noticed it. What is the best way to have a conversation with a customer to say, hey, this may be an issue. This is the steps you need to do to avoid it approaching the August, September, heat waves that we get.
The dehumidifier.
Would running the unit in dry mode compensate for some of that?
Dry mode is intended to do that very thing, but in a short time period. Like
Right.
the maximum it should be run in dry mode is like 45 minutes.
Yeah.
It's going to artificially overshoot the set point to keep it running, lower the fan speed so that it can do more dehumidification, but it's going to start contributing to, after a period of running, to safety shutdowns in the outdoor unit due to freeze protection.
Yeah. Yeah, this couple enjoyed having their double doors wide open, which is awesome. Felt great. However, my suggestion would have was more to the end of, hey, close your doors. I understand you might like the fresh air, but close your doors and start your dehumidification a little bit just early in the morning to start to just dry the room out a bit before you get into a full cool mode as the heat of the day increases. Would that be?
Well, you know, if the doors are open and the humidity by the time we heat up outside is 38%, well, that'll keep the humidity down inside the house. It might be warmer at that point, but
Okay.
that's, you know, we got some unique little microclimates everywhere you go, and they're hard to identify when you're out doing, especially a retrofit.
My buddy did this for me. Well, question. Is it unmuted? Yeah. Hello? Yes, 1 minute. Is the Kumo Cloud app ready yet? The new one?
Is that a question?
Yes. You forgot to say question mark. Question mark?
Okay, sounds like you're off in the distance. What is
He's
the
asking
question?
about he had a question. We've been having trouble with the Kumo Cloud app.
Oh, yeah, the Comfort app. You know, I gotta say, Mitsubishi is good with coming out with things and not good at actually testing them before they come out with it. My own Comfort app has problems. They know they have problems. They've told us they have problems and they're working on it.
Yeah, we just wanted because our salesmen are selling it on this.
Yeah, when it first came out, it crashed immediately and went down for a week. And then they said, don't try to connect any new ones. We have the existing ones working, but we can't solve a problem with getting new ones to work. So I'm just telling people to avoid it at the moment until we're sure it's fixed. Maybe it is today. I don't know. They don't tell us when they have a problem and they don't tell us when it's fixed.
All right, thanks.
Yep. So back to the humidity, do consider the possibility that you need another form for dehumidification other than the AC system. Something that can remove physical water without changing the conditions in the space. And it could be that simple. I don't even have to run the air conditioner, just running the dehumidifier. I know in my personal experience, 74 degrees and 40% humidity feels cold. 70 degrees and 60% humidity does not feel cold, feels hot, feels muggy. Well, look for some of our other quick hitters or other trainings. I know we're going to be kicking off that 454B training again. There's some updates we're going to make, new information we have, and we'll probably start another round of those 2-hour 454B sessions. We may break it into 2 pieces, one for the application and sales guys and one for the techs in the field, so they're both don't have to sit through the same one. That's something we talked about this morning doing. So look forward to seeing some of that and whatever other trainings we have on our quick hitter schedule. If no one else has a question, we'll end the show and you guys can get out and make some money.
Cool. Thanks, Rick.
Yeah, thank you all for attending. I had bigger attendance than I expected, but thank you.
Thanks,
And things pop up down the road, you know, give us a call at Tech Services and we'll be happy to help you.
Thanks, Rick.
You're welcome, guys.